Welcome to this explainer. Today, we're diving deep into a truly fascinating evolution in academic training. We're going to look at how we transform theoretical, on-paper research designs into practically bulletproof methodologies using AI simulations. If you've ever wondered how researchers actually prepare for the total unpredictability of field research, well, you are absolutely in the right place. You know, it's a tale as old as science itself. We spend months, sometimes years, building these perfect, pristine blueprints in the total safety of academia. But what happens when that flawless design actually hits the chaotic reality of fieldwork? Real-world data collection, institutional review board hurdles, simple human error, these things can literally shatter a fragile methodology in an instant. So we're going to look at exactly how to prevent that. Okay, here is our roadmap for today. Number 1, the quantitative research blueprint. 2, surveys versus experimental designs. 3, identifying threats to validity. 4, the AI methodological sandbox. And finally, surviving the simulation grid. Let's get into it. Our starting point today is strictly grounded in the 6th edition of Cresswell and Cresswell's research design framework. For those in the know, this text sets the absolute gold standard for rigorous methodology. Think of it as the authoritative rulebook for both human researchers and, as we'll see shortly, the AI environments we'll be exploring. Section 1. The Quantitative Research Blueprint. Every single quantitative blueprint rests on 4 crucial pillars. You need to know exactly who you are studying, what specific variables you're testing, the reliability of the instruments you're using, and precisely how you are going to analyze that data. You can't just guess here, right? If just one of these structural pillars is weak, the whole study collapses on itself. Moving on to Section 2, surveys versus experimental designs. So once your blueprint is drawn, there's a fundamental divide in quantitative strategy. On one side, we have survey design. Here, the goal is to observe and generalize trends, attitudes, or opinions from a small sample to a much wider population. It's really all about observation and inference. On the flip side, experimental design actively manipulates one or more independent variables to test a direct cause and effect on dependent outcomes. Whether you're running a true experiment with perfectly randomized groups or a quasi-experiment where you don't quite have full control, your choice right here dictates the entire rest of the study. Section 3, identifying threats to validity. But listen, no matter which design you choose, the real world is essentially a minefield of traps waiting to compromise your data. You have to actively guard against internal threats. After all, participants aren't robots. They age naturally during your study, which is known as maturation, or they might just completely ghost you, which the literature calls mortality. Then you have diffusion of treatment. Honestly, this is really just a fancy way of saying your control group gossiped with your experimental group and figured out your secrets. You've also got compensatory rivalry, where the control group feels left out and tries way harder, totally messing up your baseline. Even your instrumentation can betray you if your measurement tools shift mid-study. And you absolutely cannot forget external and statistical validity threats. Even if your internal methodology is flawless, you might face external threats, like drawing incorrect inferences from your specific, narrow sample to other people or settings. Or, on the statistical side, you might simply lack the sample size, the statistical power, to make any accurate inferences at all. To put that into perspective, a beautifully designed study with a tiny, inadequate sample size is, for all intents and purposes, scientifically useless. So, this brings us to a crucial question. How do we test this architectural blueprint against these real-world wins before we build the actual bridge? Historically, you just kind of had to hope for the best, or rely on a pilot study and cross your fingers. But today we have a vastly superior method. Section 4, the AI methodological sandbox. Welcome to the modern training ground. Let's step right into the sandbox. Now, to be clear, this isn't your standard casual chatbot experience. This is an adaptive methodological advisor. First, you initialize the environment by picking a high-fidelity AI platform like ChatGPT or Claude, which are optimized to parse complex structural matrices. You then set your horizon length, usually somewhere between 3 to 20 interactive rounds. But here is the real game changer. You are grounding the AI with strict Cresswell verification protocols. You are essentially programming an uncompromising, relentless academic auditor that will procedurally generate field obstacles specifically designed to try and break your thesis. Section 5, surviving the simulation grade. Once you initialize, you're thrust directly into the active simulation grid. When you enter, the system actually pauses right at the start at turn 0 for what we call context binding. The whole environment completely freezes until you lock in your baseline metrics, your specific research question, and your philosophical worldview, like postpositivism or pragmatism. Once you're locked in, there's no going back. Every choice you make is forced through a relentless, multi-layer iterative loop. Inside this loop, the AI is hitting you on 3 simultaneous layers. Layer 1 is the compass. Here, the AI plays the observer, dynamically altering field conditions, throwing custom data errors, or hurling angry institutional review board pushback right at you. Layer 2 is the warning layer, the methodological drift engine. This actively hurls those exact Cresswell validity traps we talked about earlier directly at your study. Like, out of nowhere, a key demographic drops out, triggering a massive mortality threat. Finally, layer 3 is the brain, the defense mandate. The AI anchors the workspace, demanding you scientifically defend exactly how you'll handle the crisis through 3 to 5 open-ended questions, and it will not let you advance to the next turn until you do. To survive this incredible friction, you need total saturation. That means answering every single prompt completely without breaking your declared scientific character. And, this is absolutely crucial, just like hitting a save point before a boss fight in a video game, you have to save your data. At the end of every turn, the AI generates a progress report code. You literally copy and paste this block of text externally. Why? Because if your browser crashes, pasting that code back into a fresh window perfectly reloads your exact variables, your turn history, and your scores. It teaches meticulous data management the hard way. If you actually navigate all these threats successfully and reach your final turn, the sandbox triggers its closing evaluation. For a quantitative experimental track, it hands you a final dataset preview snapshot. And let me tell you, it doesn't just pat you on the back and say, "Good job." It rigorously scores your statistical control efficiency and gives you a power rating based entirely on how well you defended your methodology during the active rounds. You then compile this terminal audit and your logged progress codes for your final portfolio. So, let's wrap up this explainer with a final thought to chew on. As we aggressively embrace these dynamic stress tests, how will simulating failure in a sandbox fundamentally reshape the resilience of tomorrow's scientific discoveries? By the time a student trained this way actually steps into the real field, they haven't just memorized a textbook. They've already defended their methodology against a gauntlet of worst-case scenarios. They are actively surviving the scientific process. Thanks so much for joining me today, and as always, keep questioning the data.